Right? Okay, good. So you're done with the final. Oh, no, sorry. Midterm exams. Yeah? Good. Must be happy or not happy? But yeah, it's over, right? So you don't have to think about it. One announcement. This Wednesday, meaning 2 days from now, we won't have a class. Okay, because I have to attend the KPS meeting, Korean Physics Society meeting, if I'm right. Who's going to attend the KPS meeting? Some of you who already has like research papers and stuff, or not, whatever. Okay, you guys are going. So good. So we won't have a class. And another thing that we have to decide with a little bit of pain is when to wake up. Okay, I don't think normal, regular human being sort of times are gonna work for us. We have to pick something somewhat exotic, but there are two ways to go about this. All right, I think when I check my calendar, eventually we will have to make the 4 classes. So the one that we are going to miss this week, good, because we made up last week, right? So we've been doing well. Now there's going to be 4 more makeups to do. So option number 1, we're going to have 4 separate makeups. But time is not going to be joyful time anyway, so don't forget that part. Or like we meet twice, but like intense, nice, and done like that way. Okay, so like 3 hours in a row. I mean, we can have a 5 minutes break in the middle, but then we just meet 2 evenings. So we just suffer 2 evenings, all of us. I mean, or have a nice QFT discussions, and then we will be good to go. Which one do you prefer? Time. Sorry, I don't think it's gonna work. So Friday, I think none of the Friday works, right? Okay, there's 2 options, right? Early morning, like 7 a.m. and then we have 3 hours. Okay. Or like 7 p.m. we have again 3 hours. Okay, which 7 do you like? A.m. 7 a.m. Cool. Oh, no, yeah. Okay, so then let's pick a day. Doesn't matter, right? Because it's pretty the 7, it doesn't matter which day, no?
It doesn't matter.
Because Friday could matter, right? Because you may want to go to Seoul, you have your live and good time, blah blah blah. All right, so would 7 p.m. work? Oh, which of you? Absolutely no way. 7 p.m. 2 days per semester. Okay, so it's 7 p.m. for wait, that ends at 10 p.m. Holy shit! Okay, and then I have to go for another meeting, right? Okay, so just 2 days, 7 p.m. Which of you can absolutely not come for that option? I mean, feel free. I totally respect. Okay, no peer pressure, all right? I'm not saying which day yet. Some 2 days in the rest of the semester. Just 2. We are gonna have to do some doodle surveys to pick those 2 days. Okay, good. So works. Yeah. Okay. All right. Whew. Big problem solved. Big problem solved. Then let's do that. So whoa. 4 7 p.m. but like 1.5, or like 2 7 p.m. and like 3 hours and done. Which way? Like option number 1, like 4 times. Okay. Sorry guys. It's immediately clear that it's gonna be 2 7 p.m.
I can just ask about the option as well.
But the
I think there's an option.
Okay. Wow. Okay. Option number 2, like 2 7 p.m. big party, hooray. Okay, good. All right, done. So we will definitely start computing scavengers. Okay, maybe I can even talk with knowledge if I'm given 3 hours. Okay, good. Questions from previous classes. All right, good. So today the goal is this. Okay, so primarily we will start talking about now perturbation theory as metrics. Okay, now we will eventually start talking about dynamics. so far we've been talking about like how to think about it, how to construct what is the correct thing to do, and so on and so forth. So we start building up the non-machineries to construct a way of the thinking about dynamics. But before that, there was a leftover from last class. I was desperately running, but I was stopped by the time. That means we didn't quite finish time reversal geometry that time. We covered C, and then there's a little bit left over, right? Regarding PT. So I'm gonna spend like 10 minutes to finish that up, and then we'll start talking about correlation theory and athletics. So time reversal, the punchline is that this must be realized as an anti-unitary operator. So let me just write down a couple of definitions for you. Definition number one. For instance, if there is a sum operator U, where it preserves the norm or precisely inner product in this case, then we say that the U is unitary. And definition number two. Also, if U acts on like so A, little a, B are states, alpha, beta are coefficients, and if it acts as this way, we say that the U is linear. And then definition number three. So if there is instead there's some operator omega that acts on this way. Now instead of leaving the inner product intact, instead it complex conjugated, which means that in direct notation you know that this is displayed as B comma A. So then this thing is a definition by saying that omega is anti-unitary. Now definition number four. If there is omega, again, I'm acting this guy on the linear combination of states, then if we complex conjugated coefficients, then we say omega is anti-linear. And according to Whitner, any symmetry operation can be realized either unitary or anti-unitary because in both cases it leaves the norm invariant. We talked about that. Or you can say the probability is the square of this thing, so it doesn't matter. Okay. Now I mentioned to you, I even showed a little bit of exercise back then. Unitary is necessarily linear, anti-unitary is necessarily antilinear. Okay, so they go in hand in hand. Okay, so now the problem with the time reversal was the following. So let me just write down the problem statement rather than deriving it anymore. So if time reversal is realized as some of the unitary time reversal operator, the problem number one was if I had P, Q, I. Is there a minus here or not? Minus. Okay. Do I want to put minus here or do I want to put it? Thanks. There it is. QP is I. And then if you add this guy with the unitarily realized operator, the problem was that it has the same effect as the flipping the sign, right? That was problem number one. Remember, Q goes to Q under time reversal, P goes to minus P under the time reversal, right? The coordinate doesn't change, but P is roughly speaking time derivative of the coordinate, so it flips the time, right? Problem number two, again, if I do this same thing with a time evolution operator, again, literally what this does is that it flips T to little t to minus T, right? So again, the problem was that if you do this, Hamiltonian under that transformation goes to the minus of Hamiltonian. So there's a problem because if the spectrum of this side is bounded from below, well defined, correlation theory works, blah blah blah. So this side totally screwed up. Okay, so that was the problem. And then I said that this problem can be cured if instead T is realized as anti-unitary operator, which I denoted by omega sub T. Okay, let's first quickly see how this can resolve these problems. So let's do it. Did I do this last time or not? I didn't, right? That's where I stopped. Okay. So, oh, by the way, one thing that I have to say. So remember, there's a general statement that if I want to say state goes to under U times A, this can be, well, as if there's an operator, equivalently operator that is transformed by U dagger, meaning by diagramming genuinely adjoint A U. So how do we see that? How do we see that? This is the equivalent picture. So again, if there is some expectation value that I'm looking at, right? So there's some quantum state, another quantum state, an operator. If I look at this, and then if I do the transformation U A B, obviously this can be written again as U dagger A U B. So by comparing that last expression from the first, you see that either you can think of that way, like state transform but not the operator, or you can think of this way where state doesn't change but operator transform, right? That's the equivalent statement. Now one can ask, what is the corresponding statement for anti-unitary operator? Right, you can ask the same question. In the case of anti-unitary operator, what is associated statement for operator side? Okay, the answer is, so if you have a state, and then if you do this, the equivalent statement is that now this goes through inverse that. And obviously, in the case of a unitary operator, this is equal to U inverse. So in that sense, in terms of inverse operation, they are basically the same statement. But you have to be careful in such a way that in the case of anti-unitary, you don't have dagger, like permission contract, okay, adjoint operation. So you have to stick to really what it means to be inverse operator. Let's quickly derive this result. The exact same thing. So let's look at this. A, B. So let's do the transformation. Like this transformation on state. What am I gonna write here? Literally. Now, oh, by the way, there's a fine print here. When this is true only if A is permission operator, so observable. So I can write this as A dagger omega A omega B. Okay, so let's move the A to the other side using the definition of adjoint operation, which again is the same as just A. And then I can write it as, I can stick in omega inverse like that. So let me just write that. Omega inverse A, omega inverse little A, B. Now, the way you have to read this equation is there's something acted by omega, another thing acted by omega. And the very definition of anti-unitary operation told me that this is equal to what? B. I'm not going to have that. Inverse. Where this very first line is equal to B. Oh, no, forget it. So in the sense of square of this thing to get a probability, you see that either you can think of the transforming state by omega, or you can transform the operator by this omega inverse A times omega. Okay, so this is basically the same thing for unitary case. Okay, so with that preparation now, let's think about these problems really quick, and then move on. Okay, any questions? Is that clear what I'm trying to say here? I just proved it statement. All right, so now let's quickly look at this. So there's the third one. You have to carefully use inverse rather than the dagger. So let's act it on commutator. Oh. Bless you. Okay. So again, this can be written as I mean, I can expand it first. If I had a Q P omega T inverse omega T, that is omega T inverse Q omega T, and then omega T inverse because I inserted the one P omega T. So this is basically saying that how does Q transform under time reversal? I know this is just Q and this is minus P, right? That's how you read it. So you can basically sandwich, insert omega inverse omega wherever you need to do. The left hand side will turn into therefore minus of Q dot B, right? Okay. Are you with me now? Okay, so I'm just saying the left hand side is this, but you just insert the set of omega t inverse wherever you need, so that you write everything in terms of this sandwiched version. So the net result of the left hand side must be just minus of original thing. Okay. All right. So what about the right hand side? So right hand side is also good because now this is a complex number and this must act as anti-linear operator, right? So that is minus 5. So eventually, full transformed version is goes back to yourself because you pick up the minus on both sides. So that's resolution number 1. Resolution number 2 is literally the same. I mean, it's the exact same exercise. Okay, so it's not only okay. So that's resolution number 1. That's just number 1, and 2 is exactly the same. So omega inverse e to the I, which is t, omega t, should be equal to, first of all, plus IHT. But that is the definition of time reversal transformation, right? T goes minus t. Again, you expand it out to linear order. You should find that this time, transformed Hamiltonian is plus of Hamiltonian. Okay, so Hamiltonian doesn't change. Meaning energy spectrum doesn't change under time reversal. Okay, so everything is good. You should look at this exact same. Let me just be brief about it. Any question? Yes.
So you're gonna talk about that the time reversal operator must be anti-unitary.
Yes. So good. Yes, exactly. So for these reasons, I'm saying that the time reversal should be realized as anti-unitary operator that are listed. That is there. Any other question? Okay, good. So now let's quickly look at 3 simple theory to see how this thing acts on the slot field theory. So far, it's just statement about how this must be realized. Okay, so let's consider one quick simple example. Then we move on. That simple example is our friend. 3 real field theory. Now, T goes minus T without flipping spatial part. And then P flips X part to minus 9 without flipping temporal part. And you see that if you combine these two, PT basically flips the momenta to minus the momenta, right? So you flip both all of them together. Now, as Hong said, we're gonna just do PT instead of just T separately. And the reason is because, not because we cannot talk about T separately, but simply because if you combine PT together, the transformation is manifestly Lorentz-Invariant way. Okay, you just bring the all four momenta together. Okay, so we're just gonna talk about this. Let's ask under this P and T, how does the state transform? Okay, let's ask under the P times T, how does the state P, which schematically is created by some break operator. Sorry, vacuum. Let's ask how that transforms. So the question is how this state transforms by the combination of P and T. Now let's think about physics way. So first of all, I had a particle with a momentum P. And then this is the derivative of x with respect to t. So it has one factor of x, one factor of t. Right? So under the P transformation parity, x flips. So it goes that way. Right? This is a mirror symmetry. If there's a particle coming that way, the mirror says that there's another one that's coming that way, right? Opposite direction. So now if I do the T transformation, this time I flip the T without touching x part. Again, it flips the momentum. That's because if there are a particle that's moving that way, if I run the video backward, obviously we'll do this, right? So in this case, it flips again. So it goes back to P. So the combination of P and T leaves the P momentum invariant. Okay, so therefore, one can say that P, if it acted by omega T UP T, that is invariant up to possible phase. So let me just put some possible phase because it is quantum mechanics. Okay. Some of you want it. Okay, so that's all good. Now, you should ask yourself whether you can rephrase this statement in terms of creation and annihilation operators. Okay, the creation and annihilation operator has a single label. In this case, just the momenta 3, momenta p. Right? So if I just I'm just thinking whether I have to simplify this notation. Are you creative? What can I use for this? What can I call? N. Oh, that's terrible. N. No, that's number operator. Give me some idea. Q. Oh, that's chart. So
What about C?
C. The C is so fancy. If I write the C here, I can do that.
That's O.
O.
Right.
PT. Thanks. Done. So O. Ooh. So O. Oh my God. PT inverse A. I do that without that doesn't matter. In P, therefore, we will leave it invariant like that. Again, of possible phase, but let's not worry about that. That's not. Okay. So you might say, oh, looks like the combination of PT acts trivially, right? It doesn't change the state at all. But it doesn't change the state at all if you stick to the momentum space picture. You can ask yourself whether that's true even in the position space picture. Okay, let's ask that question. So in quadratic field theory, which is real, this is real and then free. You know that field operator is realized as this. Alpha P. Okay. Now, here's one question to all of you. By now, are you all happy and comfortable with going back and forth between the two, or are you sick of it? Like, I don't want to deal with that. Okay, hopefully you're okay with now seeing both of them, right? They're just related by normalization factor, right? 2 pi to the bond in the square root of 2e. Then you could put it, right? Okay, good. So you see, now let's ask how this operator behaves under the this beautiful OPT. Okay, so let's do that. So OPT inverse pi of x PT. Now, that doesn't do anything. This is just a number which are real, even. That doesn't do anything to this, nothing to this because of this fact. But then this combination is x as if it is anti-linear operator, right? Oh, for that, let me just write a one multiplication table. Okay, U denotes some unitary operator, omega denotes some anti-unitary operator. So you use U, omega. So you have a product of U and U that behaves like unitary and linear. Okay, if you have a one vector of omega and U, that behaves like anti-unitary, anti-linear. Okay, and now you can just quickly fill it up like that. Okay, in other words, if you do the complex conjugation twice, you go back to yourself. So keeping this in mind, you see that the only non-trivial action here is on this complex phase, right? Because this combination acts as anti-linear operator. So you see that, therefore, it has an effect. If you just sandwich it, this has an effect of changing this to the I plus I t dot x, and then you flip this side to that. Right? So whole effect is as if it's to the minus IP of minus x, and this is equal to plus IP of minus x.
If the OPT is anti-linear, then doesn't that also conjugate complex conjugate alpha p as well?
Well, alpha P is just the AOP, and I showed that's the product of the combination of the PT leaves in invariant. And I argue that based on this statement, if there's a state with a momentum P, the combination of the P and T leaves that is invariant. And that is created by AP. So it should leave AP invariant. So now I can just write down the answer. So therefore, this should be phi of minus x. Again, possibly up to some base factor, which I'm not keeping track very carefully. Okay, that makes sense because I just told you already. PT should move x mu as vector to the minus of x mu, so it does that job. You shouldn't surprise, but you should be happy. Okay. But obviously, this is scalar field. So if you have a vector and spin half and so on, there will be more complications. Okay, so but we're sticking to the scalar field. Any question before I move to now for division theory and scattering? Yes.
We usually consider the combination of the discrete symmetries like CP and PT here and CPT. My question is, why don't we consider CT?
Why we do not, or why do we do?
Why we do not consider CT invariance?
Oh, no, good. So you can, in principle. Since there's a question, let me just say one fact. So, the first of all, I arranged it. See, there's like at least the 3 ones, but you can have more. Okay, in principle, in quantum field theory, you can have more than just this set of discrete symmetries. Okay, you can have all sorts of discrete space transformation or swapping transformation, all kinds of that. But for now, let's just focus on these 3 just for a second. Then fact number 1 is the CPT combination of CPT should be a symmetry of the. Okay, and in fact, one of the beautiful results coming from what is known as axiomatic quantum field theory. What is axiomatic quantum field theory? There are a set of super mathematically talented people who are interested in quantum field theory, trying to set the quantum field theory as a mathematically rigorous thing. Okay, and people started doing that, and then they made some progress, super rigorously mathematically. One of the things that they were able to show is that CPT must be symmetric. Okay, there's a little book, but good luck. If you pass like 5 pages, come to me. Okay, I mean not that I try hard. Anyway, so it is a symmetry. If this is even there has been a work like showing that this is a same statement as a Lorentz symmetry. I mean, there is some work, but I haven't read much of it. But I've heard of the statement. So that's statement number 1. Now, statement number 2, but from the questions, then you can ask more sort of questions. For instance, can I talk about the CP invariance? Then per this statement, you know that the CP invariance is the same as the P invariance, right? Because the whole product is symmetry. If you violate this, you violate that, right? In such a way that the product is symmetry, right? If you flip minus sign here, you have to flip minus sign here so that the whole product is +1. Okay, so for instance, if you are interested in CT, do it, but that's same as asking parity violation. Okay, so therefore you have heard a lot about the parity violation, but not necessarily CT violation because they're equivalent. Okay, and some of you heard of what's known as a strong CP problem. That is same as asking a strong T problem. Okay, and so on and so forth. Okay. I'm gonna raise everything, but you can ask questions. Yeah.
At the when you do the E minus IPX and at the OPT field, then wasn't the X get flipped to minus X at there because of the PT?
You mean this?
No, and X gets flipped by minus X and the OPP is and the unit is so.
No, so are you good? So the way I worked at this is for an operator.
No, I mean the E minus IPX.
Here.
Yes.
Yeah, so if I sandwich here, I have to ask whether how this transform, how that transform, right? Then you know how everything transforms.
Yes.
I already know how this transform. I already know how this transform because they don't transform. It's real numbers. And this is a complex number. I know that this should flip to the side because this is anti-linear operator.
Yes, so I also agree that that also flips the minus I to I because it ended linear, but
Exactly.
it's because popular OPP, so the PT flip X to minus X, right?
Oh, good. So you see, I've been taking the Heidelberg picture all the way through that. I'm not touching like, a state part. I'm not just worried about how operator transform, and then I just, you know what I mean? So the way I work that here is the how state transform, and then I translate that into how operator transform. But in order to understand how this operator transform, I use the fact that my knowledge about how this operator transform, modulo the fact that this is anti-linear transformation. So I'm not making active transformation of space part. Okay, I'm just now looking at the operator dressed with some C number part.
Oh, so that's a C number.
Yeah, exactly. This is a C number part. This is linear combination of operators with the complex number coefficient. Okay, just like what I read there. Like there's state with linear combination and so on.
Okay, got it.
Okay, good. There was a question? Yes.
Time reverse time version operator
Yeah.
and is acting on the some operator, then like Hamiltonian, then we calling the time reverse Hamiltonian is equal to the Hamiltonian at minus time t or the Hamiltonian at t, but the operators consisting of the Hamiltonian is reversed.
Okay, so good. So the question is, if there is a Hamiltonian, like which I think you're thinking the Hamiltonian, which is a function of explicit t time.
Yeah.
Right. So then the question was, given that if I do the time reversal transformation, does that mean that this is Hamiltonian related to original Hamiltonian at the same time, or it is related to the original Hamiltonian at minus t? That was your question. I think you're asking that question because previously I said that in the context of parity, if there is a field operator, right, I'm comparing the parity transformation of that operator is some sort of linear combination of operator, but at minus x. So that part I think should be the same. That part I think should be the same. We just said so far the thing that we've been considering here in today's discussion. I assume that the Hamiltonian doesn't have explicit time dependence there, right? Because that's why I wrote previously that like e to the minus I t t, and then if I do this, just goes to this because it's t goes minus t. You assume that obviously this doesn't depend on time. That's why I wrote it. But if there is, you have to take that into account. And then you're going to relation of the Hamiltonian at like t to some linear combination Hamiltonian at minus t. Because if I just write this way, this equation is not right because this is not a good equation. I'm going to show some equation today, hopefully, that time evolution operator for Hamiltonian that has explicit time dependence, that unitary operator is not just either IHT. That's what I'm saying. So that's why I don't want to just replace it with a H of T. But morally, conceptually, that's why you should get if you have done it correctly. Okay, let's now move on. Now, next thing we want to talk about is correlation theory. And salary. And the rest of this course will be occupied by the discussion of this, like how to think about it, how to do it, how to compute it, how to understand digits, and so on and so forth. And then also the second QLT, in addition to this, now you're going to learn more ingredients, like how to do correlation theory in a more sophisticated, more proper way, and so on. Okay, there's a loop diagram, there's radiated corrections, there's renormalization, and so on and so forth. So you're going to learn all those techniques in QLT2 class, and that's usually what is taught in most of, in fact, all QFT 1 or 2 classes everywhere in the world. And that is another reason why you may heard that the QFT is a very large subject, and learning that part is not covering much of the QFT space because we're explicitly tackling the question of perturbation here. And there's a lot of non-perturbative features in QFT, like QFT features that cannot be captured by just looking at the perturbation theory sense. Okay, that's the sense. The topics of the QFT is fast, and but that's how you start. Okay, because you don't have any techniques to tackle to solve the QFT exactly. So you have to learn how to tackle the question like in a small perturbation and how to expand things around the well-understood piece. So that's the thing. So we are gonna first talk about perturbation theory and then gathering, and eventually, hopefully, we're gonna talk about what is known as F metrics. So the first thing I want to talk about is Schrödinger picture. There are 3 pictures: Schrödinger, Heisenberg, and interaction picture. Probably. Okay, so we're gonna spend some time quickly talk about this. I think in the QM class, quantum mechanics class, probably you learned it. So I'm just gonna label stuff with F, H, and I. Okay, so let's talk about the F picture. Not to be confused with the F matrix. This is the Schrödinger picture. So here, states evolve in time, but operators are time independent. And in H picture, Heisenberg picture, your states are time independent, but operators evolve in time. So let's first talk about this quickly. So what do I mean by that? Well, suppose I have a state, some quantum state in the quantum mechanics sense, and then suppose I look at the state at time equals 0 sense. Okay, so remember, there is this time evolution in the universe, right? And then if there's a sense of defining the time fluid, then I can define a temporal slice, meaning there's a space, and then we can define a Hilbert space. And then I can define a state at time t, in this case, for instance, by time equals 0, time equals 0, and then I can evolve the time using some unitary operator, u, eventually I will introduce. And then I want to have an operator acting on this Hilbert space, and then I have an operator acting on that Hilbert space, right? And I want to ask, how does the dynamics work out? So in Schrödinger picture, let me just therefore put subscript as, given a state at 0, then a state at t, you want to get it from some time evolution operator. Like that. You have seen this, right? Good. Or if you like, you can write more generally. If you have some time 2 times, you can connect it. Is unitary operators. On the other hand, I said that the operators doesn't work. For instance, if I had the Schrödinger picture operator t, that is the same as at time t or any other time. Now, where the rules come from? Looks like it's cooked up rules. I'm not happy. You can ask, why should I accept this at all? Right? Oh, you're totally happy to accept whatever. Okay, totally open-minded? No, you shouldn't be, right? In science, you should be conservative. You should ask why. Why? You should ask all the time, right? That's how you become strong. So what do I mean by all of that said? What I mean by is the following. Suppose I am in the sometime slice t. I can't even know exact what time you're talking about, but at some slice, I'm dropped, I'm observable, I'm given a state, I'm given an operator, and then I can say, oh, I cannot spit a meaningful observable at the time. So like I can compute something like this, right? I can look at the expectation value. Now, let me write this equation twice. Okay, so that's manifestly true state. Okay, it must be happy. But that must be true regardless of the picture I pick. Like if I ask the question in shredding picture, if I ask the question in algebra picture, for that matter, I can write yet another equation with label little I, a big I here, right? Picture is human beings or theories way of analyzing the system. But whatever you do, it should all match. Observables must match. Okay, now in this language, let's think about what I mean by this. Okay. So then I can make one decision saying that, oh, I just want to think about entire time evolution be dumped into the state rather than an operator in a way that this quantity doesn't change. Okay, so there will be, so if I say this is little a of t, some observable, right? Real number observable. And then I will just understand entire time evolution or time dependence coming from how state changes, right? That I have a freedom to do so. So long as I don't change the meaning of this. All right. So therefore, in shredding the picture, which you usually learn in quantum mechanics, you learn that the state. So let me just write first without anything. So you learn that things evolve like that, right? This is the shredding equation. This is how that guy got very famous. Probably got Nobel Prize too. Not probably. That's how you got Nobel Prize, right? So that's good. Okay. At the moment you start writing wow, he's getting a Nobel Prize. So good. So that's the equation. Now I'm saying this equation has name. Shredding equation. So shredding equation. And let me be careful about H2. So H is a function, as we learned in canonical quantization, is a function of generalized variables like P and Q. And so I better put S2. So I'm in the single one sort of picture now. Okay. And then in principle, this guy can have explicit time dependence too, in principle. All right, so good. Then this equation combined with this interpretation, meaning entire time evolution is dumped into the state evolution rather than the operator. Then if you just plug it into this equation, you should get I. But just to be clear again, let me be precise, you say everything is assuring the future. Now I will make use of this equation basically now. Okay, good. So before the little list, key properties of this time evolution operator. Now, what you would be interested in understanding? You are interested in understanding the dynamics of quantum systems, right? If somebody hands you a system, you want to understand what is the state at a given time that you're given. What are the possible observables you can possibly measure? Magnetization, I don't know, temperature, pressure, whatever. And you want to know how that thing changes because of internal dynamics, right? So that's what you want to understand. So in terms of a theoretical language, therefore, what we are interested in this picture is that I want to understand how states evolve over time. Why is that? If somebody has your initial state, and if somebody tells you that you should be able to measure the temperature, where is it? Temperature or magnetization, then you can measure the entire change of the temperature, pressure, whatever, the observable. that is 100% fixed or determined by this operator, right? So in this language, in the quantum dynamics is 100% captured by determination of this operator. Okay, so that is 100% information stored there, not the initial condition. Right? So what are the properties of U that have to satisfy? First of all, there are periodic equations that you really have to just solve this equation, right? As I told you, if I know this, you know everything. So that U has a couple of properties to satisfy. First of all, U is unitary. Why is that?
No concern.
Good. Probability has to be preserved. Right? So probability preservation says that U have to be unitary operator. And so this mathematically does mean that inverse of U is the same as A joint. Right? If you remember U there we use for the one. So property number 2. So that has to be sensible. So if you go from the T double prime to the T prime and then continuously going from T prime to the T, obviously they should be the same as operation. You have learned that. Okay, why is that? Since this satisfies linear equation. This is a linear diffusion equation. That's why this linearity property is satisfied. Okay, time evolution is completely linear. All right, it sounds like I go faster and then changes to much faster and slow. There's no such a thing, right? So it is linear. Good. Number 3, I did write down it satisfies that dynamic equation. Or initial conditions. It means that U over T of T should be 0. Again, because of the linearity of the equation. Okay. Now, from equation 2, combined with the 4, meaning if you set here T is equal to T double prime, that's what I meant. From this initial condition, that's 1. That just tells you the following thing, right? The inverse of T prime is the same as flipping it over of argument, which makes sense. Right? Time goes that way, inverse of that is going the other way around. And that is also related to the fact that this is now unidirectional. This is from the unitary part. Okay, so these are the properties of the time evolution operator. Okay, so that's the Schrödinger picture. Now, let's use this equation to move on to the Heisenberg picture. Right? I told you that in Schrödinger, entire time evolution is here, but Heisenberg, instead you put every time evolution here. So there's a matching point. So this should be, I mean, I guess you all know this. So if this is too boring, I will be quick. So matching condition is the following. First of all, state at t equal to 0, Schrödinger should be the same as Heisenberg state. And the operator at time equal to 0, Schrödinger picture should be the same as Heisenberg picture. And in the case of Schrödinger picture, then it stays as arbitrary time. Because I told you that this doesn't evolve. Now this principle, right, this statement that the physics shouldn't change regardless of the choice of the picture, there will allow you to connect these two pictures. Okay, so let's do it real quick. So let's see if this space is enough. Okay, let me actually erase this part. Do it. All right, so let's do it. So Schrödinger picture, measurement at time t, some operator as Schrödinger picture. So that is equal to Schrödinger picture sine of 0, u bigger t 0, as 0 again because Schrödinger picture doesn't evolve. The u t 0. Okay, so let's write down the definition of the state at time t in Schrödinger picture. Now, matching that is equal to Heisenberg picture state And then again, that says that this is safe in Heidelberg picture. Now, this measurement, I'm just measuring at what time? So that's the question. And also remember, this is the same as in Heidelberg picture, this is the same as time t, because in Heidelberg picture, state doesn't involve. So I'm making a measurement at time t in Schrödinger picture. That should be the same as measuring the same thing in Heidelberg picture at the same time t. Right? So that was the physics principle. So again, this is the same as h. So what that has to appear here is nothing but Heisenberg operator times t. Because that is the requirement for the physics work. Okay, I can choose two different pictures: Schrödinger at time t, Heisenberg at time t. That should match. So by comparing this, you see that therefore the Heisenberg operator evolves time according to that relationship. Okay, so you're used to it, but then nevertheless now we can determine it here. Okay, so now any questions so far? I'm going a little bit fast here because hopefully you have seen this at least more than once before. Okay, but if not, nevertheless, at least I think I contain at least all the content you need to know, so you can go back, read it slightly more slowly. So now from this equation, now we can determine the equation that this thing has to satisfy, right? There's a time evolution for A of this operator in Heisenberg picture, right? We had a dynamic equation for state that was described in the picture. Yes. Right? So then you can ask, in Heisenberg picture, what is the equation that is the counterpart of this? Right? Because in Heisenberg, it is an operator that runs. So we can derive it from that equation. So let's do it. How do I do it? Well, that is weird looking. Okay. So let's just write T. I'm interested in how that changes. Well, there's a definition of it. So let me first write this big equation. U dagger T 0, A is 0. Remember that is the same as A is 0, U is 0. Okay, now you act here and there, right? So let me just write U dagger T 0, then A is 0, and then U. Good. So now you're done because you know what this is doing, right? You already derived equation for U. Did I have that? Boom. Okay, here. Okay. Since you know how U evolves, in this case, minus IHU, and this will be what? Conversion conjugation of that thing, which is plus I U dagger H. Good. So we can just write down the answer. That's right here. So this is right picture. No. Any operator like P, Q, whatever runs according to that. Well, I'm running out of space. U. Right? Okay, now let's complete it. So this comes with that. If H doesn't have explicit time dependence. Let me say that again. This is made of H. Right. And if there is no explicit time dependence, that is basically e to the minus IHT. Right? So H commutes with itself every time. because it doesn't have explicit time dependence. So U comes with time, H. If again, H doesn't have explicit time dependence. Right?
Yeah.
Good. So now I can pass. Now like a sandwich. So that will give me H, U dagger. Oops, I'm running out of this. Equals that, right? So what is that there? Here. Good. So here we go. That's our dynamic equation, and you have seen that. That's Heisenberg equation. Shredding equation for shredding a picture. Heisenberg equation for Heisenberg picture. Okay? And you see that in both cases, the key object determined is still U, right? In both Heisenberg and Schrödinger picture, dynamics is captured by the U. Okay, so now I'm gonna move on to interaction picture. Well, any questions before I do? Okay, so let's do it. Okay, so now interaction picture, you should be a little bit more alert. Okay, you can miss it, you can lose it. So wake up now. If you've been sleeping so far, that was fine. Now interaction picture. And as we will see, interaction picture is a picture. You can invent your own picture, but interaction picture is an all picture in which perturbation theory can be set up very nicely. Okay, so that's why we want to talk about it. In either shredding a picture, Heisenberg a picture, which is a totally good thing to do, but you have to determine the U at one shot, which includes an entire Hamiltonian. So that is like saying, can I just solve the complete QLT completely? If you do so, like done, right? Then you can use whatever picture you like, doesn't matter. But in most of the cases, solving quantum field theory exactly is almost impossible, notoriously difficult. There are a few exceptions, because miraculous exceptions, where genius people manage to solve it exactly. Okay, but most of the cases it's very hard. So getting this U like exactly is very, very hard. The question is whether there's a nice picture where there's a good notion of solving it in an approximate way. Okay, so that's this interaction picture that up. So here, interaction picture. Now operators. Okay, before that, let me actually set up the stage. So suppose somehow your total Hamiltonian, which in shredding picture. So for now, I'm starting with the shredding picture. Suppose in shredding picture, your total Hamiltonian have to be that there's this P and Q and even explicit dependence. But then it turns out that suppose it can be decomposed into H dot part. And then something else. I haven't specified what is the division between the two. The only requirement for now is that the total Hamiltonian has a piece which doesn't have explicit time dependence, and you can solve this part exactly. So that is the function. And then the rest, which can have or may not have an explicit time dependence. Let me say it again. If the theory structure is in such a way that there is some piece that you can solve exactly, and then the rest. Therefore, overall, you cannot solve exactly. Okay, that is the stage. Now, most of the cases where this is applied is when you have a field theory where you have a free part, like the free scalar field theory. And then some interaction. For instance, you can have lambda by 2 to the 4th, eta by cube, whatever. So this is quadratic theory, you can solve it exactly. But if you start adding this, you cannot solve the entire thing exactly. Okay? However, let me stress this one more time. this division, which is most of the time applied to the free versus interaction part, is not the only way this picture is going to be used. Okay, so in principle, let me say that again. If the theory structure is in such a way that some part, maybe free part, maybe not, but that part you can solve exactly. And then something else. This picture is applicable. Okay, so for now, I'm not going to commit to this particular decomposition, but I'll just imagine there's some decomposition. Now, in interaction picture, operators evolve or by this part that can be solved exactly. And then states evolve how. So let's determine that. Okay. So again, in this picture, I just set them in such a way that our operators evolve by this exactly solvable part. And then let's first determine then how state must evolve. Okay. And let's see whether that equation looks useful or not. Are you with me? Am I lost? Okay, I realize that I have to no. If I go this pace, I might be able to get to the point that I was planning on. But I don't know. So I don't know. I mean, there are materials that I want to cover, and there are clarity I want to deliver. There's always this competition. And anyway, that's it. But you have to stop me, right? If you start feeling like this guy is going away alone, you have to stop me. Okay, there's no point of just say a lot of things which doesn't make any sense. Okay, so question. Good. So then let's see how state must evolve in this picture. And by now, hopefully, you know how to determine that. There's this physics principle, right? Observables must be same in every picture. That's how you determine that, right? So let's set that up. Ready the picture? There's some operator. Let me just even write it as t equals 0 because I know that each ready the picture, that thing doesn't apply. And first of all, let me say what I meant by this operator part. What I meant was if there's some operator in interaction picture time to the t, right? I said that it evolves only according to h. What I meant was it does interaction picture 0 to the minus h. That's what I meant. Right? So I demand that in this picture somehow operators transform under the time evolution only by this way. Okay? So I demand that, and then I will determine how that thing will transform to match that this should be the same in both pictures. And then we will look at that to see why that can be useful thing to do. That's the plan. Okay, so here let's do it. First of all, here, well, I demand that should be equal to interaction picture t. Interaction picture t. That's I demand. And from this, I will determine how state must transform. Let's do it. So first of all, on this side, turning the picture to 0, the U dagger is 0. So this is the full. This is controlled by the full dagger formula. So the shredding picture now. And then there's again this is full. Good. So that I just wrote what I meant. Okay. And then let me write the right hand side. This means interaction picture state at time t. And then I told you how this thing transforms if that's either I t a I 0 Okay, done. Now let's look at that whole thing. First of all, this state is the same as interaction picture state at time equals 0. That's the matching point. Okay, let's look subscript. Right? So that's the matching point where state coincide at time equals 0. All operators coincide at time equals 0. So that means that this is also the same as the interaction picture operator. Okay, so now if you compare both sides, now you should be able to read off the UT0 turning picture is equal to e to the minus I HT interaction picture. Okay, so what that means is that interaction picture state at time equal to t is equal to e to the I h naught t u. Now I'm just gonna put interaction picture because that's the thing. So that's how they evolved in interaction picture. Now let's understand the meaning of this vision. You can fill out the detail. I literally just use that, right? And then use the matching point right off the equation. Now let's see if that that agrees with our intuition. Then you can ask which intuition. Okay, what intuition? Let's go back here. There's total time evolution controlled by h naught plus h prime, right? That's the entire time evolution. I said that operators transform only according to h naught. Super naively, you might think, oh, the state should evolve only according to h prime. Naively, super naively, right? There must be some notion of that division. Okay, exactly how it is divided, let's see. So say the interaction picture starting from time equal to 0. First, oops, run by total time evolution. Okay, oops, that was not what I was expecting. Then let's go backward, only by h naught. So very naively, super duper naively, but I would like to criticize momentarily. If you think super naively, this is like big quotation. Don't quote me, don't zoom me. So if that looks like minus I total HP, you sort of have a sense, right? Okay, I'm just handling effect phenomenon looks like it is evolving according to h prime. Okay, just that level, but not quite exactly so. Okay, so let's make that part slightly more clear and precise. But it's very interesting mnemonics at the very least, right? If you're like, oh, okay, I have to remember how interaction picture state evolve. Oh shit. So I have to start from where? Like lecture number 1. But you can quickly just remember, right? And let's just go full or make mistake and let's correct it by h naught. Okay, so but then let's determine slightly more careful. So one thing that I'm gonna do is the following. So first of all, I can set it up the dynamic question. Okay, say the time equal to t. I'm just gonna set it up in such a way. Oh, I just want that this is controlled by a unitary operator in interaction picture. That belongs from time t prime to t. Okay, you can put 0 here if you like, but that's what I meant. Okay, so then you can say, oh, you already know what that needs to be. That is this thing. That is that thing. Although there's a little bit of mismatch because of like time equal to 0 versus that, we can fix that. So at the very least, so here in this picture, therefore, the key object that I'm interested in determining is this thing. Why is that? The assumption was this h0 part is completely solvable. I understand everything about it, right? So I know how operator transform. Therefore, I just need to understand how they transform. Then I know everything how things transform. And the entire evolution is controlled by this single operator, which is nothing but this. Okay. So now let's determine what kind of equation this thing needs to satisfy. Just like Schrödinger picture, state, Schrödinger equation. Heisenberg picture operators and Heisenberg equations of motion. Interaction picture, this part is clear, right? Because I know everything about it. That's the assumption about it. So therefore, rest of the evolution is controlled by this. I want to derive the equation that determines how this evolves, right? That's the next thing I need to know. Then every single picture, I have an evolution equation. I just need to solve it. And that's where we will start seeing that this picture will be useful for perturbation gear. All right? That's clear. Let's do it. So, well, I can just take a product here, or take a product here. So let's set it up. So let's consider the case where t prime equals 0 for now. Again, it doesn't matter, right? Just for the sake of it. So here ui t0 is, again, this is cool. I'm stressing out many times. So is equal to first that thing. Well, I want to move in actually. Not that it matters. I want to move in. And then second time. Okay. I just did it. So you know how this transforms. That's shredding the picture thing. Tell me. And I can tell me. That and you. Let me, for the sake of it, let me put. Right? Okay. So let's wrap it up. All right, so therefore, minus I H H 0. I mean, if you want to write it, and then U. Right? Good. Good. So now, so that I can write everything in terms of use of I. Right? Let's use the definition or determination. So e to the minus plus ht, e to the minus I ht. That's 1. So then minus I times e to the I h naught t, e to the minus h I h naught t, instead using this thing, some operator. And then the rest is ui. What is that thing? There's an operator, and then evolving only according to h naught. What is that thing? So let's remind you. So if I have a t as, right, operator, and then if I do this, what is that thing? I just call it a, oh, oops. Right, interaction picture thing, right? So this is some polynomials of p as p, q as whatnot. And then if I just sandwich it, you know what to do, right? You just stick in all these factors somewhere. Everything, convert everything into interaction picture. So therefore, overall, this equation turns into minus I. And that is what? H prime. Yes? Good. So then let me just write it again. So interesting. I'm important on that. Let me just write it again. Okay, so now you convert this thing into what? Interaction Hamiltonian there's an interaction, so have H prime in interaction picture, that's what I meant. Okay, and then U prime. Good. So that is very nice looking equation, but you know, it's nice looking because I write this way, like with nice little big I here. Looks like, oh yeah, I think everything is I. Well, you have to accept what you mean by that I. Okay, so remember when we talk about this, and then when I said the things like saying operators evolve according to H naught, we naively expect the state evolve according to only H prime sense, right? But that now has been made precise. The state evolves by this operator that is controlled by H prime, but not down H prime, right? It's slightly fancier H prime, and you pass that onto the interaction picture H prime. Okay, good. So that's the evolution equation. Now there is a key here. If you pass on to the interaction picture like that, then yes, that is exactly identical looking equation that we already talked about for Schrödinger picture equation. But this now is time dependent no matter what. Let me say that again. In the Schrödinger picture, we had a moment of joy that say, let's assume H does have explicit time dependence. That's great, okay? And then we just write down nice equation that looks like this. But now in interaction picture, that thing is always time dependent because I evolved, even I drop this part, even if I drop this part, I evolved according to the time. So you have to be not careful in writing down the solution to this equation. Okay? Good. But it's great because you singled out this H prime piece. That was the trouble part for you, right? That precisely because of this H prime, you could not solve the QFT exactly. That was how I set up the question. But now you singled it out. Okay? Good. So far, this is the exact statement. I have not talked about any perturbation yet. This is called the exact statement. All right, now let's move on. Like 2 more minutes. Okay? Because I want to write down important equation now. Just 2 more minutes. I promise. But I don't have to keep my word, right? I promise, but I have to keep my word. So then solution. Now you just write down this solution. Like T, let me now just reinstall the T prime. But say, okay, I know how to write down that solution. Now I will be a little bit fancier because there's T time dependence. Now I'm trained person. It's gonna be smart. Okay, this is pretty good looking equation, right? This is slightly more sophisticated than just writing down H dot T, but I'm now carefully integrating over. All right? Okay. But this is not gonna work. This is the wrong equation. This is not the solution to the equation. And the reason is because the explicit time difference, if you just expand it out, right? If you just expand it out, there's a lot of HI at different times, but they don't commute in general. Why? This is a function of now P's and Q's at different time. P, Q doesn't commute. So you can't just move around. When you write equation that looks like this, you have like HI to the power. I'm gonna pull out the first HI out and then recombine the rest of it right as U. But like which HI you have to pull out in this equation? Exact time T that you're looking at the T of UI. But these are not, doesn't commute, you cannot just move around, right? So because of that feature, as I stressed it out, this has explicit time dependence, this is not the right answer. The right answer is this. Hold on, I'm not ready yet. Okay, so, well, you can demand that I design my symbol such that this is the right answer. You can say that I do, but I already introduced you time ordering symbol. Now it's great because now why? Because I need to pull out the HI with a specific t. The t that is the latest time in this equation. Because I'm looking at from the sum time t prime to the t, where t is the latest time. If I demand that, I can always pull out HIT because that is the latest time, and according to time order, I have to pull that to the leftmost. Right? So that is guaranteed to work now. I'm pulling that out. I'll prove this is the solution next time, but this is the solution, and we're gonna spend this time. But then this is the key object. This is the master equation. Okay, we have to play it. All right, so I will have to stop here. Any question? All right. You have a question, hold that thought. I will meet you outside, okay? Because we have to go out.